Uh, Now we are going to discuss the stream function, potential flow, potential function, and the irrotational flow. Potential flow and irrotational flow, it is two words for the same phenomena, which is mean there is a flow and the flow is not rotating, so it is a potential flow or irrotational flow. Okay, stream function and the velocity potential function. Velocity potential function is its definition is the rate of change or uh, it is describing the velocity with its direction. For example, if I said that is the potential function for an x direction to u, it is meaning that in dx, in dx, in this dx, the potential function has been changed, which is like this. In another word, that velocity multiplied by the distance, it is equal to the potential function. It's a definition like this. Okay? For example, for v, the potential function, the velocity potential function, it is equal to the velocity in v direction multiplied by y. Okay? Of course, it is v multiplied by dy because when the velocity start to move in y direction, the velocity change. So it is v dy. Okay, this is the definition of function function. What is the benefit of it? Later on we're going to discuss, but just grasp that definition. Okay, now the stream function, which is maybe a little bit we are similar in it, is what is the change or what is the change, for example, in u, which is in x direction, in the vertical axis, which is mean in case of this streamline have a function, which is mean, for example, let's assume this streamline is a parabolic. So the streamline, which is a parabolic, for example, which is having a stream function or equal constant. So this is a constant. Its definition is the velocity, for example, in x direction, the velocity u multiplied by dy. So in another terms, the rate of change of the stream function by vertical axis is u. In another word is stream function itself has a relation with flow rate. Okay, which is mean it is has a relation with the flow rate. So if we have the stream function, so you have an idea about the flow rate. Of course, we are talking about 2D, so width is infinite width. And the potential function is the same. So let's, based on the description, and we're going to understand what is the what is the benefit of it. So the velocity equal to potential function in x direction divided by del phi potential function by del x, and v is del phi by del y. The stream function del psi by del y. The velocity function, it is minus del psi by del x. Based on this definition, of course, this is the polar coordinates or cylindrical coordinates, and which is r and theta, and this is Cartesian coordinates. It is about 2D. 3D, it is way complicated. Okay, so even this one named as potential function theory or irrotational flow series. There is a long derivation to get this. Okay, but it is okay. We're going to understand what is okay. There is another derivation or another pieces we need to understand that the rate of change of that rate of change plus the rate of change for the other rate of change is equal 0, which is mean the gradient of phi equals 0, which is mean the second derivative, partial derivative of phi by del x square plus del y square, it is equal 0. Same concept for psi. Why it is in relation to the continuity. Del u by del x plus del v by del y equal what? Equal 0. So second derivative is the second derivative here, is the second derivative here to apply continuity. So you will have second derivative del phi by del x square, del square phi by del y square should equal 0. Okay, because the first derivatives are equal 0. Same apply for psi. Same if you're going to use polar or cylindrical coordinates. There is something else named vortices or vortices, which is also a definition. We name it like this, like an eta z. It is del v by del x minus del u by del y should be equal 0. And it's the same if you have cylindrical coordinates. This defines that there is no vortex, So the change in v in x direction minus the change in u in y direction should equal 0. And at least at the end, the Bernoulli, but the simple form, which is b over rho plus v square over 2. V square is the magnitude of the velocity, which is u square plus v square under root. Gz, the potential, is equal constant. Now we are just writing some definitions. We will go understand now what is the use of it. See, assume that we have, we're going to have blocks. Assume that we have a linear uniform flow. Good enough? Yes. So we know that based on uniform flow, there is zero velocity in V, zero velocity in Z, and we have only velocity in U, which is U equal capital U. And from the above definition, we can write it, that is U equal del phi by del x, and also U equal to del psi by del y. From this equation, integrated, so phi equal ux plus c1. From this equation, integrated, psi equal uy plus c2. We can always assume c1 and c2 equal 0 because it is defining from where you start and from where you end. I don't care. I will assume that I start from this point and I will assume this point is the 0. And for the y direction, from you start to I will assume I will start at this point and this point is the 0. So we always can assume c1 and c2 is equal 0. So based on, and because also we know that v equals 0, so del phi by del y equals 0 and minus del psi by del x equals 0. Now there is a very important point. While we already defined phi and psi, there is one condition in the CFD or in the fluid mechanics. The rate of change in the directions can be added, not the magnitude. The rate of change in the direction can be added, like the velocity in x direction plus velocity in x direction can be added, but pressure at x direction and pressure at x direction cannot be added. Remember Taylor series. Okay, so rate of change can be added, which also give us that is phi is the rate of change in x direction and psi is the rate of change of y and x, and so we can add the rate of changes. Keep it in mind. If we check source and sink, forget about the derivations, but at the end we're going to have phi with something, psi with something. Of course, we'll assume c equals 0 and c2 equal 0, but we're going to have phi equal this one, and we have here phi equal this one. Add this one and this one, you can add it. So in case if I have, by a scenario, that is I have a uniform flow, and in the middle of the uniform flow I have a sink, which is mean like a tank, and the tank has a hole. So to simulate or to have the function of the velocity, I'm not going to use Navier-Stokes equation. Huh? I'm going to use the potential flow theory, which is stating the fluid is not rotating. So I can add this one, and I can get phi equation and psi equation, and I can get u and v. So this is the main idea. And because we know that is psi is already the q or the flow rate by the width, even I can understand what is the flow rate. Let's go in deep in the source thing. We know this is v. We're going to use Cartesian coordinates because you see there is theta and there is r, so it is better to use Cartesian coordinates. So you are, I'm just going to take it from here. We'll take the Cartesian coordinates. So we'll take this equation, sorry, the polar coordinates. We'll take this equation and we'll go to here. So it is very, very simple that the velocity is equal to ur, the velocity in r direction. Er is not e, which is 2.7, no, it is like I and g and k. That's it. So ur in the velocity in r direction, the velocity, rotational velocity. You will tell me now it is rotating. Just keep with me. Keep with me. In theta direction plus the velocity in z direction. We know that is the velocity is not rotated. It is perpendicular in the center point, so this is 0 based on the definition of irrotational flow. And z, it is, we are dealing with 2D, so z, I don't care when it is reach here, there's a black hole or whatever, but here also there's 0. So v equal ur in the direction of er. Just for us, we need to define something for the sink and source. If the flow out, flow in. If the flow in, so it is in positive. If flow out, it is in negative. Okay, so now we can define that is v equal this, or it is equal the flow rate multiplied by 2 by r, now it is parameter, multiplied by the length, the depth in the paper. So assume it is cylinder and there is depth in the paper, like this. Assume it is cylinder and there is a depth in the paper, and flow is going like this. So the flow rate is the parameter multiplied by L, the length, 2 by r. This is the flow rate. Okay, this is the area. So this is the area of the flow rate itself. Okay, so flow rate divided by the area is the velocity. Just for a quick um, approximation, or not approximation, for quick writing, we are naming magnitude. When we are dealing with this theory, we are naming a magnitude. Magnitude, it is the flow rate per unit length. It is 2 by m. Q by unit length is 2 by m. So we can write that is magnitude is equal to, so we can write that is V equal m over r. It is just an expression. Now we know the UR, so d phi by dr equal UR from here. D phi by dr is equal UR. Make the integration. So make the integration. So oh, and epsi by the way, and epsi d epsi by d theta 1 multiplied by 1 over r equal mr. It is from here for the epsi because I have only UR. So based on this, so phi equal m ln r integration, and epsi equal m because r by r theta because I make integration in theta. This plus constant 1 plus constant 2. We also assume that this constant is equal 0. Now you're going to tell me, okay, now we create something we don't know, or you told me, or I told you that is if you have two cases, you can add it together. So how I can add ux and uy with r and theta? Very simple. R equal what? R equal, forget this is change of axis, shifting of axes, but r equal x square plus y square, theta equal tan inverse y over x. This is clear, it's normal. Okay, now I assume that is the flow in the center of the uniform flow in the center of the flow. Of course, it's not the case. Maybe sometimes you're going to have maybe maybe you will have some uniform flow like a wind, and there is a sink here, or like a pipe giving a flow, and there is a hole in the tank. So we know that is the water flow will go like this, like this, like this. So this will be the stream functions. Okay, now if I put x and y here, so I need to shift this x or y because the potential function, extreme function, is built on this one. Okay, so to shift from this point to this point, the axis. Okay, now we are going to follow this concept that x here and x here, if I want to shift this x here from x here, forget that as I have x and b or r. So this x, which is start from here, and this x start from here, from A, from B. Okay, so x due to this function is equal to x here plus b. Okay, and in the opposite case, and in the other case also as well, that is y here is equal to y here plus a. This is y by the way, this is mistaken by this is y. Okay, okay, so r if I go, for example, this is in polar coordinates, so I want to shift it like this, so r equal y plus a squared x plus b squared. So if I am going also to change from Cartesian coordinates to polar coordinates, always it is better to change from polar to Cartesian. Okay, but however, we're going to check it later. So this is how we're going to shift, and also the same. Tan theta is y plus b y. This is, so I just corrected. So it is x plus a squared and y by b squared, and the same y plus b x plus a. Okay. Now we're going to check the examples. You will understand when you have example. If you have a vortex still is not swirling. It is a uniform flow, but it is going like this. So it is still not a vortices. So it is still a uniform rotating flow. Okay. So we'll use the same VR, V equal VR, ER, EC, EU theta, and 0 in the direction. We know from this definition that is the vortices should be equal 0, which is mean, and UR should equal 0. In this case, we don't have any, we cannot have a velocity in vertical, otherwise it will be rotational flow. Okay, so del, which is based on this, UR equals 0, so UR equals 0. When UR equals 0, so 1 over R del epsilon by theta, or del phi by equal 0. Written back here. So you will find it here, del R theta, mu theta, by del R equals 0. Same. This one, the vortices equation. Okay. And of course, this is u theta. I will convert it again. Okay. Equals 0. So from this, r theta equal constant, because r u theta is not changing in r, so r theta should equal constant. Okay. Or do the integration. It is plus constant, so it will be 0 multiplied by r, which is 0 plus constant, so r u theta equal constant. Also, we have something like the magnitude. It is similar like the magnitude, which is 2 by like a magnitude. So q over L equal 2 by magnitude, same 2 by magnitude. It's the same concept, but this was minus, because uh, it will be easier for us for the solution later on, you'll understand. So this will be equal by theta, because we know u theta is a flow rate, and the flow rate can be described like this. And from it, we understand that is phi equal u theta, integrate or differentiate here d phi, it is r u theta del theta, r u theta del theta equal phi, so integrated, so it will be r u theta theta equal to phi. طيب r u theta is this one and theta. So it is just manipulation of the writing because r is gone here. Okay, and psi also equals this one. Okay, this rules is for integration and derivatives. We are going to use it, but this is mathematical. I'm not going to explain it. We're going to, when we need it, we'll explain it. There is Rankine half body. Also, it is a combination, which is we stated. It is an example. Source, linear flow. It is can be simulated like this. So here it will be like a wall due to the streamlines. And this is a separation point, just the definitions. We know that is psi equal psi1 plus psi2 as we agreed. So from it, psi1 is what? Is a linear flow. Y, U, Y, U, Y. And we know that is this one is thing, which is psi equal m theta. M theta. So psi equal V. Here we see there is Y, V multiplied by Y and m by theta. Either you're going to convert theta to tan inverse or to convert Y to R sine theta. Which one you're going to do? Of course, to make it r sine theta, otherwise you will have y and tan inverse y over x. So try when you are trying to make a derivative or integration, it will be a nightmare. So this is just a logic thinking, okay? Okay, so we have the stream function. Okay, this is very good. Apply conditions. So at B, we know that is u theta. It is total stagnation. U theta should be equal 0 and u r equals 0. We know about this this point. So u r is equal what? U r, its a definition. U r equal 1 over r del psi by del theta. Del psi by del theta differentiate theta by theta by theta, which is 1 over r r cosine theta and m. See if we are going to have Cartesian coordinates and we're going to differentiate, make derivative for in x direction, and the x direction has tan inverse y over x. It can be done as here. So tan inverse y is a constant in respect of derivative of partial of x. So it can be done here, which is mean what I'm trying to state is this method can be, but it will be minus y over x squared plus y squared. Okay, both is the same. So UR equation, we can get it. So we can get the velocity function of r. Repeat the same for psi at r. It will be minus del psi by del u theta del psi by minus del psi by del r. Differentiate or make derivative for this one. It is all constant except r. It's very simple. So it's not this VR, it's not r. So it is all is a constant. So it will be minus r sine theta. And that's it. So let's return back. There is here just a small mistake. R will go by R here. And for this, the derivative is v by r, so it will be v sine theta. R will be by y. So here there's no r, it is v sine theta. And this one is r by r, so it is v cosine theta plus m over r. Okay, so this one also v. So this v and this is v, this is not r's. So based on this, apply the boundary layer. So u r equals 0 when you can write it when r equal minus m over cosine theta, and r is the distance from this point to this point. Okay, and u theta also, when you put u theta equal v sine theta equal 0, so it is only in case of theta equal 0 or pi of 2 pi. So that's it. And of course, we already understand that from any definition of the flow, from here, that is Q over L equal to 2UML, 2UM, M we know it, we approximated before. It is 2 by Q over 2 by M is equal M. So based off on that, and we already have this equation, so we can get it. Okay, so we can remove M, but Q, so at a certain flow rate, I can understand from where is the stagnation point. So like this, if we have a source flow pipe open and there is pipe giving water, without anything, I just can know where is the velocity equals 0 without doing Navier-Stokes, without doing anything. Doublet, I will keep it later. There's no benefit to discuss it now, but I will keep it later. We'll go to the example in the next session.